Let's dive right into this fascinating explainer where we're going to decode the highly logical and honestly pretty elegant world of organic chemistry. Look, if you've ever stared at a massive chemical name and felt completely overwhelmed, you are absolutely not alone. But today, we're going to break it all down using a really simple concept, a family tree. We'll trace exactly how basic, foundational molecules transform into an incredible variety of substances that make up our entire world, literally just by swapping out a few atoms.
But before we get bogged down in formulas and math, we have to remember the physical reality of what we're talking about here. We aren't just moving letters around on a whiteboard. We are talking about physically re-engineering the actual building blocks of matter. I mean, changing a single bond can be the difference between a totally harmless liquid and a highly reactive solvent. To keep us on track, we'll be following this roadmap. We'll start with the world of hydrocarbon derivatives, move from alkane to halide, explore alcohols and ethers, dive into the carbonyl family, unpack molecular isomerism, and finish up with standard enthalpy of formation.
All right, let's kick things off with Section 1, the world of hydrocarbon derivatives.
The absolute key concept you need here is the functional group. Think of a basic, unreactive hydrocarbon chain like a blank canvas. A functional group is like taking a highly specific, vibrant color of paint and splashing it onto that canvas. It completely changes the picture. It's just an atom, or maybe a tiny cluster of atoms, but the second it attaches to the chain, it instantly dictates how that whole molecule is going to behave. By simply swapping in one of these functional groups, we can take a basic, odorless gas and turn it into a complex liquid, or even an ester that smells exactly like bananas. It's wild.
Moving right along to Section 2, from alkane to halide. This right here brilliantly shows off the mathematical logic of organic chemistry. Everything stems from our base molecules, the alkanes, or as they are perfectly categorized in our source material, al-alkanat. So how do we build a new derivative? Well, we take our parent alkane, which follows the formula CnH2n plus 2. We mathematically drop a single hydrogen atom, which leaves an open attachment point, and then we swap in a halogen atom, which we represent with the letter X. That halogen could be fluorine, chlorine, bromine, or iodine. And the result? Boom! We've just created a brand new chemical family, the alkyl halide.
Now, because chemists are all about efficiency, we use a handy shorthand notation for this, Rx. The R is just a leftover hydrocarbon chain from our starting alkane, the alkanate base we just mentioned, and the X is our newly attached functional group, the halogen. This simple Rx formula, it's literally the blueprint for countless industrial chemicals you use every day.
Next up, Section 3, alcohols and ethers. Okay, what's truly mind-blowing here is how the exact placement of just one single oxygen atom completely rewrites a molecule's entire destiny. If the oxygen pairs up with a hydrogen to form a hydroxyl group and attaches to the very end of the carbon chain, you get an alcohol, which is ROH. But if you take that exact same oxygen atom and wedge it between two separate carbon chains, acting like a bridge, you get an ether, or ROR'. Same exact atoms involved, but totally different placement, which means completely different chemical and physical properties.
And you know, the structural nuance doesn't even stop there. If we just look at alcohols, depending on exactly which carbon that hydroxyl group attaches to, we can classify them even further. If it's on a carbon attached to only one other carbon, it's a primary alcohol. Attached to two others, that's secondary. 3, tertiary. Each tiny variation subtly tweaks the molecule's boiling point and its reactivity.
All right, let's jump into Section 4, the carbonyl family.
When a carbon atom double bonds to an oxygen atom, we get the carbonyl group. And because of that double bond, and the way oxygen essentially hoards electrons, this specific structure is incredibly reactive. It acts as this vital anchor point, the backbone really, for creating some of the most important chemical families in both nature and industry.
By simply changing what's attached to the left or the right side of that central carbonyl group, we generate an unbelievable amount of variety. Attach a hydrogen, you get aldehydes. Attach two carbon chains, ketones. Pop an OH group on there, you've got carboxylic acids, like the acetic acid sitting in your kitchen vinegar right now. Attach an oxygen and another carbon chain, you've just made esters, which give fruits their sweet, aromatic smells. It is a total masterclass in modular design.
Which brings us to Section 5, molecular isomerism.
This introduces a seemingly impossible question. If I hand you the exact same number of carbon, hydrogen, and oxygen atoms, shouldn't you always build the exact same molecule? Well, no. Actually, no way.
This phenomenon is called isomerism, and it is an absolute cornerstone of understanding organic chemistry.
Take the formula C4H10O as a puzzle. If you're just looking at the raw count of atoms, it's a mystery. Depending entirely on how you arrange those specific atoms, it could be built as a hydroxyl-bearing alcohol, or, if you sandwich that oxygen right in the middle, an ether.
This perfectly proves that in chemistry, it isn't just about the ingredients you have, it's about exactly how you connect them together. They're like Lego bricks. C3H6O could be an aldehyde or a ketone. C5H10Br2 could have the bromine atom sitting on the exact same carbon or on completely opposite ends of the chain. Structure literally dictates function.
And finally, Section 6, Standard Enthalpy of Formation.
So why do all these structural shapes actually matter? Energy. The standard enthalpy of formation tells us exactly how much heat energy is either absorbed or released when these specific molecular bonds are formed from their raw elements. Notice the negative signs here? That tells us energy is being released. These are exothermic reactions.
Look at aluminum oxide. It has a massive enthalpy value of negative 1676 kilojoules per mole. This vividly highlights the sheer, incredible amount of raw energy locked away inside these chemical structures. When those specific bonds form, a tremendous amount of thermal energy is unleashed into the environment.
Even something as common and stable as liquid water has a significant enthalpy value of negative 286 kilojoule per mole. Every single molecule, depending entirely on the functional groups and bonds we've spent this whole explainer discussing, has its own totally unique energy signature.
Which brings us to the ultimate question. We've seen how, from a simple, humble base of alkanes, our alkanates, we can engineer an endless, branching tree of derivatives just by swapping functional groups and rearranging isomers. So, I'll leave you with this thought. If simply swapping a few atoms can change a molecule's entire identity, its state of matter, and its energy profile so drastically, what untapped chemical power is still waiting out there to be discovered? Thank you so much for exploring the chemical family tree with me today. Keep analyzing, keep questioning, and keep learning.